Hello again. Thanks for studying math with me and watching this video. I'm reminding you again, this is useful to have a pencil and paper in hand and to use these so you feel comfortable with the material we're covering. We're going to continue our discussion of damping with a couple of more examples. And so here's the first one that we're going to take. We take, again, the spring and mass system from the first example, but we're attaching a different damper to it that will exert a force of 17 pounds when the velocity is 2 feet per second. And again, we want to find the displacement at any time t, called u of t. So the only thing that really changes this time, although it is significant, is that the coefficient, the beta, instead of being what it was earlier, it ends up being, let's see, 17 over 2, so we get that expression. And so this is a different, this is going to be a d squared plus 17d plus 36 this time, and the same initial conditions as before. And so this is a different differential equation. And instead of having a double root as we had before, this time we're going to have two distinct real roots. And they're going to be negative 17 plus or minus square root of 145 over 2. And again, we're pretending to be engineers. So this is minus 2.4 and change and minus 14 and change. That means that the solution looks like this, with those as exponentials being added together, a linear combination of them. And when we plug in the initial conditions, we end up with these as the coefficients. And note that now we have two distinct real roots. Now when we look at the curve, for this, we see that, that we have kind of a similar behavior to before, but the general situation that we're looking at here, since we had two distinct real roots, was that the discriminant was greater than 0. Now in this situation, we say the system is over-damped because the damping coefficient is large when compared to the spring coefficient. And so the corresponding solution is that when you're using M1 and M2 to represent the roots, or if you're using it in terms of the discriminant, you could write it this way. And the curves are going to look like this, or in our case, what we had was those coefficients ended up being negative, and so we ended up being underneath the axis rather than above the axis. Now, so that's overdamped, and we will look at another example of a different kind of damping. This is when we take the spring and mass system, again from the first example, but for this example, the damper exerts a force of 5 pounds when the velocity is 2 feet per second. Again, we want to find the displacement at any time t, called u of t. Now, this time we find that beta is equal to 5 over 2. This is the differential equation that we come up with, and it becomes this. When we multiply all the way through by 2, we have the same initial conditions as we had before, but now we get roots that are complex conjugates of each other. Minus 5 plus or minus I times the square root of 119 all by 2. So that means that our solution is going to be e to the minus 5 over 2t times the linear combinations of cosines and sines, having this as an argument. And what I'm going to do is I am going to figure out what those coefficients are, and I get these as the coefficients. Now again, this time I am going to be changing this also into the cosine representation, so we know what the amplitude is. I do expect you to know how to do this. So the amplitude is going to be that coefficient squared plus that coefficient squared, which ends up being this number here, 0.502096, I guess, and the arctan of that ratio. Now this time we're looking at an arctan that is positive, so that means either it's going to be in the first quadrant or it's going to be in the third quadrant, and we have to figure out which one. We figure out which one the same way by comparing these coefficients up here, and so we conclude that it is in the third quadrant. So it's a little bit more than pi, And so we end up with this number here, and the answer to this is u of t is equal to 0.502096. That's e to the minus 5 over 2t. It's a cosine of the square root of 119 over 2t minus 3.2321. And the picture looks like this. Now you notice that this is the first time where we actually have had some oscillation. You might think about you bringing your car to a stop and it bounces up and down when you stop if your shock absorbers aren't very good. So this goes up, but then the damping ticks down, and what we have is we do have oscillation, but eventually the damping takes care of that oscillation. Now, such a system, and you remember that the reason we got the sines and cosines was that the discriminant was less than 0. So lambda squared minus omega squared is less than 0. In this case, we say the system is underdamped since the damping coefficient is small in comparison to the spring constant. The roots m1 and m2 are now complex. In fact, they're complex conjugates one with another, and this is what they are. And you can see that the undamped system that we had is being compared here to the underdamped system. And so we do have it damping out, but we do have oscillation because this is underdamped. More later and soon.